Greetings. This is Graham Warren working with you on the coffee cart case study. We're working on an AnyLogic model. We've got it laid out here in front of us. I want to just go through the details with you. So in this model or in this case study, there are two types of customers. It's really a single queue serving two types of customers. I'm going to cut over to the PDF to show you what's entailed here. We've got espresso customers coming in at the rate of 3 per minute, latte customers coming in at the rate of 1 per minute. The squared coefficient of variation of the inter-arrival times of these two streams is not 1. That means they're not Poisson processes. So, they have an unspecified distribution with this rate and with this squared coefficient variation of the inter-arrival time. For the service distributions, we've got the rates. Rather, the mean is 10 seconds for the espresso customers, 50 seconds for the latte customers, and then the service times have squared coefficients variation 0.25 and 0.16. It's possible to go ahead and figure out what the standard deviations of the inter-arrival times are for both types of customers, as well as the standard deviations of the service times for both customers. In fact, that's what we're going to need here. So just know that, in the actual case study, the distribution of the inter-arrival times and the service times are unspecified. And so we have to make some sort of call to actually implement this in software. And that's what I've done. I've assumed that they're normal, but with a truncated normal distribution. What's going to happen, the reason for that is in a normal distribution, we could have negative inter-arrival times or negative service times. And of course, that's not practical, in the world. So we'll just slice that off, truncate that at 0. And, basically what happens there is the software goes back and tries to find a new, sampling and samples that is the normal distribution and new instead of taking the negative value. Okay, so the way this is laid out is you can see that espresso arrivals are going to run through this top sequence of blocks, and then the lattes are going to run through the second sequence of blocks. What connects these guys is a barista pool. There are two baristas serving these two streams. So this is essentially conceptually identical. So I'm just going to go through the espresso arrivals. I've selected here a truncated normal distribution for the inter-arrival time. I want to just expand that for you. Perhaps I can slide this all the way to the left here to get that to show. Yeah, there it is. So it's truncated. The minimum value is 0, the maximum value is infinity, and then the mean is 20, and the standard deviation is 16. So I went ahead and figured out what that standard deviation is for the for the espresso inter-arrival distribution. And then once they've arrived, they line up. There's a timer, so I'm going to basically go ahead and figure out the timing system for the espresso customers and then for the latte customers separately. Unfortunately, it's not going to be easy to get sort of an aggregate timing system here. But what we do know is that espresso arrivals occur at roughly 3 times the rate of latte arrivals. So when we wanted to figure a time in the system, we know 3/4 of the traffic are espresso arrivals. So we'll take 3/4 of the waiting time in system of the espresso folks, 1/4 from the latte folks, add those together. And that's going to be our estimate of the expected average, the average timing system across both types of customers. All right, so the espresso folks show up according to a truncated normal distribution approximation for the inter-arrival times. They line up. Once a barista appears, they grab that person, get their espresso prepped, and then they release the barista back to the pool. And of course, the barista can go ahead and serve, whoever's next up. And this barista pool is serving both tracks here, the espresso folks and the latte folks. Okay, so once the barista has been released, we're going to stop the watch on them, and let's just see if I can slide this over a little bit. For some reason it's not wanting to slide. Let's see if I can. There it is. Here it is. Okay. I want to show you the end of the process here. So you can see that once the barista is released, we stop the timer, and then we sync or we exit those customers. Same concept here. The espresso prep has got a normal distribution on it as well, truncated one. So min 0, max infinity, mean of 5 standard deviation of, mean of 10 standard deviation of 5. And then very similar here, just different arrival time distribution parameters for the latte folks, as well as the service time distribution folks, service time distribution. As far as the statistics are concerned, I am picking up, I'm using this statistics block here to get, I'll just show you what's entailed there. I'm getting the espresso queue and I'm figuring the average size. So I'm going to go ahead and capture that. Also want to get the utilization of the barista pool. So if I click on this, you'll see barista pool utilization, and I'm going to capture that. And I'm also getting the average queue size of the latte folks. And then finally, I've got two distributions, and these, this first one here comes off of it's the timing system W sub S for the espresso folks. The second one is for the latte folks, and then it's going to be up to us to take that average, to compute that average. 3/4 of the folks espresso folks, 1/4 of them are latte folks. You can do the math, get a average across both types of customers. So that's the model. I want to go ahead and run this for you. Now, as with any one of these models, you'd want to do 3 runs to, and then average or, process the results to obtain a confidence interval. We can run it slow initially, just to see what's happening here, and just watch the number of folks exiting. So there's about 20 here, about 6, 5, 6, 7. So that relationship of about 3 to 1 is holding up. Of course, there's randomness built in here, so it's not going to be exactly a 3 to 1 relationship, but in the long run, that's what we're expecting to see. And you can see that the pool is about 58, 59% utilized at this time. Is this exact? No, because I've used normal truncated normal distributions to approximate those inter-arrival and service distributions. So there isn't sort of like an absolute final answer here, because you have to do some sort of approximation for those distributions. You can see that the average time in the system for an espresso customer is very, very short, in the ballpark of about 14 seconds. They show up, they get it, they're out. Whereas the latte customer is sticking around for about a minute. Now I'm going to increase this so that we can get all the way through. I mean, you want to do fairly deep runs on this. I think I'm allowing up to 30,000 espresso arrivals and 10,000 latte arrivals. And so I will stop it somewhere out there. Let me stop it now. Oh, that wasn't a good move. Let's try that again. Just run that fast. Pause it. You can see how stable these estimates are, and they seem to be relatively stable already, but I'm going to run it out a few thousand customers just to be sure. See, this one here has relatively long tails. There are a few customers that are presumably getting stuck behind some of the latte folks here too. So right-tailed right skew distributions. All right, so we're up to about 1,500 now on the espresso, about 580 or so on the latte folks. I'll let this go just a little bit longer. The fact that we've truncated those distributions also is another approximation that is going to impact our results, of course. So I'm going to stop it here and see that, it's about 20 seconds for the espresso folks, a little over a minute for the latte folks, and you'd take 3/4 of the 20 seconds, 1/4 of the 66 seconds to get our estimate. Okay, so that's the coffee cart model.